So let us welcome in next lecture of MAT-601, that is real analysis 2. So in this lecture we'll start chapter number 5, that is Fourier series. In previous lecture, so we have seen definition of Riemann integral, then some properties of Riemann integral. So in the chapter, so we'll first define Fourier series, and then so we'll find Fourier series of some particular functions. So before defining the Fourier series, so let us see some important results. So which we required for calculation of Fourier series or to find Fourier series of certain functions. So first result, so I can write it as a theorem. So first theorem. So statement of this theorem is that actually I am writing this theorem in form of formula or just statement of theorem, and we will prove just single formula, and remaining formula you can prove at home, or proof of this are same as one. So statement of this theorem is that first, see, so integration from minus pi to pi of cos kx into cos nx dx, so that is equal to 0. So whatever values of k and n. So for k, n equal to suppose 0, 1, 2, it goes to, and here k should be not equal to n. So if k and n are different, then always the value of this integration, that is minus pi to pi of cos kx into cos nx, is always 0. So that is first result. Second result, so integration from minus pi to pi of cos square, you can write nx dx. So if this k and n are equal, so then what happens? In that case, that will be just cos square nx. So what is that integration? So this integration is pi for, so n varies from 1 to, so here for n varies from 1 to up to, it goes to infinity plus infinity, and its value is 2 pi if n equal to 0. So when n is 0, then value of the integration is 2 pi, and if n is not equal to 0 and it is greater than 0, so in that case the value of this integration is pi, just pi. So third result, that is integration from minus pi to phi of sin kx into sin nx dx. So value of this integration is always 0. So whatever values of k and n, so k, n varies from 0, 1, 2, it goes to plus infinity, and here k should be different from n, so k is not equal to n. So that is third result. Fourth result, it is, so integration from minus pi to pi of sin square nx dx, and the value of this integration is always pi. So if n equal to 0, so naturally if you take n equal to 0, so that will be sine 0, and in that case value of this integration will be 0. So otherwise always, so value of this integration is pi. So here, so n varies from 1 to 3 and it goes to plus infinity. Basically n equal to 0, then directly you will get the value of this integration 0. So next, that is fifth. So what is integration of? See, integration from minus pi to pi of cos kx into sin nx dx. Value of this integration is 0 always. So whatever values of k and n. So if you take k and n equal or different, whatever it is. So k and n varies from, so you can take 0, 1, 2, 3, it goes to plus infinity. So these are the 5 statements of this theorem. So I just write all these 5 statements in a single theorem. So we'll prove just first result, and the proofs of remaining are same as 1. So proof of this theorem. So proof. So we'll prove first. So all these results can be derived from appropriate trigonometric identities. So you can use all these results. So first I will just comment and then I will continue the proof of first. All these results may be easily derived from appropriate trigonometric identities. So we'll prove, for example, we'll prove just first, and you can prove. So remaining using same technique. So appropriate trigonometric identities. So for example, see, so we'll prove first. So to prove first, so we can use these trigonometric identities already. So all we know, that is cos. So what is cos kx plus nx? So cos a plus b. So that formula you can use. So it is nothing but cos kx into cos nx minus sin kx into sin nx. And similarly, second, what is cos? So kx minus nx. So these elementary identities you can use and you can prove one. So this is nothing but cos kx into cos nx plus it will be sin kx into sin nx. So let us see. So if you add these two, so adding these two identities, so what we will get? Adding these two identities, so we can write. See, so what we can write? So left hand side will be, that is cos kx plus nx plus, that is cos kx minus nx. And you can observe the second term will be cancelled and it will be 2 times, that is cos kx into cos nx. Or simply you can write it as, so alternately you can write, or so what is cos kx into cos nx? So it will be half times this, that is cos kx plus nx plus cos kx minus nx. So this is the resulting identity which we have to use in proof of 1. So here you can suppose k is not equal to n. Otherwise, so it will be just cos square nx, and so that will be second result. So here suppose that k is different from n. So k is not equal to n. So integrating, so you can write this equation as, suppose, or identity as 1. So integrating, see, 1 from minus pi to plus pi. So we get, so what we get, let us see. So it will be integration from minus pi to pi of, that is cos kx into cos nx dx. And what will be this side? So you can take this half outside of integration. From each integration you can take, and it is integration from minus pi to pi of cos kx plus nx dx, and that will be half times again integration from minus pi to pi of cos kx minus nx dx. So you can integrate these two integrations. So usual integrations. So what is value of first integration? Let us see. So it will be half times, so integration of cos, which is sine, so it will be sine kx plus nx, and it's divided by k plus m, and its limits are from minus pi to pi, plus what is second integration, that is half times, it is again sine, so it is kx minus nx, and it is again divided by k. So you can take this x outside of kx minus nx, so it will be, so k minus n, and the limits are from minus pi to pi. So let us see, if you put, suppose upper limit, that is pi, so at x or in place of x, so what it will imply, it will be imply pi times something, or that is k plus n pi, and we know what is sine pi or sine n pi, that is 0. Similarly here also, so you'll get term sine n pi, and similarly for lower limit, that is minus pi. So both upper limit and lower limit, values of upper limit and lower limit will be 0 in both terms, and so therefore resulting integration will be 0. So you can see, so value of this integration is nothing but 0. So that is, so what we proved, integration from minus pi to pi of cos kx into cos nx dx, so this value is 0. So remaining proofs are similar to 1, and you can prove so this at home. So this proves 1. So you can write, this proves result 1. The proof, you can write, the proofs 2 to 5 are similar to 1, hence, so hence you can do, or you can complete these proofs at home. Hence you can complete it at home. So this is proof of this theorem, and we have from this theorem, so we have these 5 results. So again I will just revise these 5 results. So what are these 5 results? Let us see. First result, integration from minus pi to pi of cos x into cos nx. So cos kx into cos nx, integration from minus pi to pi, so this value is always 0. See. Second, if this k is not equal to n, if k equal to n, then what happens? So it is nothing but just integration of cos square nx from minus pi to pi. So in that case, the value of this integration is equal to pi if n varies from 1 to up to plus infinity, and value of this integration is equal to 2 pi if n equal to 0. So if n equal to 0, then value of this integration is nothing but 2 pi, and if n strictly than 0, so in that case the value of this integration is equal to pi. So this is second result. What is third result? So it is again same. See, so if, yeah, so integration from minus pi to pi of sine kx into sine nx is 0. So where k is not equal to n, and k n both varies from 0, 1 to up to plus infinity. So in that case, the value of this integration is equal to 0. And if suppose n equal to k or k equal to n, so in that case this integration, so resulting integration will be minus pi to pi of sine square nx dx. So in that case, the value of this integration will be pi for n varies from 1 to and it goes to infinity. Or still you can modify this result. So you can write, so value of this integration equal to pi if n varies from 1 to goes to plus infinity, and that is equal to 0 if n equal to 0. If n equal to 0, so then it will be sine 0, that is 0, everything is 0, so it will be 0. So it is not necessary, so that's why, so I have not written it. So fifth result, that is integration from minus pi to pi of cos kx into sine nx. So here one term is cos and second term is sine, so cos is multiplied by sine. So in that case, again its value is 0 in both the cases. That is, if n equal to 0, still its value is 0 because second term will be 0. And if n is not equal to 0, means both k and n are different. And yeah, so, and having the values 1, 2, 3, 4 goes to plus infinity. So in that case, again its value is 0. So this is statement of this theorem and the proof of 1. So next, So further I will write some more results. So first, that is definition of odd function and even function. So first, so it is definition, and it is definition of, suppose, even function. Yeah. So what is even function? So definition of function f on. So you can take interval from minus pi to pi. So f is a mapping. So it is defined on the interval, suppose minus pi to pi, is said to be an even function. See, if it satisfies the following condition. So what is condition? So f of minus x should be equal to just fx. It is true for all x belongs to this closed interval minus pi to pi. Means if x varies from minus pi to pi, or x lies between minus pi to pi, the value of f of minus x should be always equal to f of x. So in that case, we say that f is even function. So this is the definition of even function. Yeah. So this is the definition of even function. Next, so you can simply write some examples of a even function. So for example, let us consider, see, first, so fx equal to, suppose, x. So is it a even function or odd function? So here x belongs to minus pi to pi. So I'm taking this interval minus pi to pi. So function is defined on this interval minus pi to pi, which is a subinterval of set of real numbers. So here, what is f of minus x? So let's suppose fx equal to x. X belongs to minus pi to pi. So here f is an even function. So why it is an even function? You can simply check it using definition. Since, see, so what is f of minus x here? F of minus x using definition of fx, so that will be just minus x. Sorry. So here you have to take x square. So it will be minus x its square. So what is minus x square? It is again x square, and which is nothing but fx. So here you can check fx equal to x square. X lies between minus pi to pi, is an even function because it satisfies the definition of even function. What is the definition of even function? F of minus x should be equal to fx. So here f of minus x, that is equal to minus x its square, which is x square, which is nothing but fx. So that is, you can write, that is f of minus x equal to f of x for all x belongs to minus pi to pi. So therefore you can write, so therefore f is an even function. See, so this is one example of even function. So similarly you can take another example. So let's suppose I'm taking fx equal to, simply take cos x. So here x belongs to minus pi to pi. So check whether this function is even function or not. Yeah. So here again f is an even function because you can check the definition of even function. See, so because what is f of minus x? So f of minus x will be cos of minus x, and you know what is cos of minus x? So which is cos x, and which is nothing but fx. So that is, you can write f of minus x is equal to f of x, and it is true for all x belongs to closed interval minus pi to pi, and therefore this function satisfies the definition of even function, and hence fx equal to cos x is an even function. Hence you can write, hence fx equal to cos x is an even function. So these are the examples of even function. So furthermore you can write some more examples. So third example you can write. So let's suppose fx equal to x raised to 4. So here x belongs to minus pi to pi. So here f is an even function, and simply you can check it. Also you can write some more examples, so you can do it at home. So next definition, that is definition number 2, and it is definition of odd function. So next definition, that is definition of odd function. See, a function f on closed boundary interval minus pi to pi is said to be odd function, is said to be an odd function if it satisfies the following condition. If f of minus x should be equal to minus of fx, and it is true for all, so x less than equal to pi and greater than equal to minus pi, that is x belongs to this closed interval minus pi to pi. So this is the definition of odd function, same as even, but a difference is that, so in even f of minus x equal to fx, and in odd function f of minus x equal to minus of fx. See, so this is the definition of odd function. So we can simply write some examples of odd function. So for example, let fx equal to x, and here x lies between minus pi to pi, so x less than equal to pi and greater than equal to minus pi. So here you can observe f is an even function. Here f is an odd function. You can simply check the definition of odd function. So what is f of minus x? Since f of minus x is nothing but, so it will be minus x. I'm using definition of fx because definition of fx is fx equal to x. So using that definition, so f of minus x will be simply minus x. So I can write it as minus of x, and it will be minus of x means minus of fx, because x is nothing but fx. So that is you can write. So what is the meaning of this? So f of minus x is equal to minus of fx, and this is true for all x belongs to minus pi to pi. Hence you can write, yeah, so it gives that f is, or fx equal to x is an odd function in the interval minus pi to pi. So this is one example, and similarly you can consider other examples. So second example you can take. So let's suppose fx equal to, I'm taking sin x, and you can check it is again odd function. So here x belongs to minus pi to pi. Third example you can take. Suppose fx equal to, you can take x cube. Here x belongs to minus pi to pi, and likewise remaining also. So you can check these are the examples of odd function. So next I will write some remarks on this odd and even function. So next I will write it as a remark or results. So first remark is that, see, so remark first or note one. First remarks, first, if f is an, see, if f is an even function, let us see, then what is the integration from minus pi to pi of fx? So then integration from minus pi to pi of fx dx will be equal to, it is 2 times integration from 0 to pi of fx dx. It is very simple, simply you can check it. So why this remark is there? Because, so in bracket I can write since so since f is even function, what is the definition of even function? So definition of even function is that so f of minus x equal to minus fx. So using that, so what will be this integration? Integration from minus pi to pi of fx dx. You can write it as integration from minus pi to 0 of fx dx plus integration from 0 to pi of fx dx. See, so here, so you can replace this integration. So here you have to put suppose x equal to minus 1. So if I put, I will change color. So let us put here, put, so x equal to suppose minus 1. If you put x equal to minus y, then what happens? So here, if x equal to minus pi, so y will be pi. And what will be resulting integration? So that will imply, let us see. So in that case, first integral can be written as, so it will be phi to 0 and it will be f of minus y because we are putting so x equal to minus y. And what is dx? So dx will be minus dy. So that will be first integration, and second integration will be as it is. That is integration from 0 to pi of fx dx. So let us see. But what is f of minus y? So since f is an even function, and you can take this minus outside of integration, so it will be pi to 0. So it is f of y and it will be dy plus, that is integration from 0 to pi of fx dx, or still you can change it by y or as it is. So fx dx, since here f is an even function. So since f is even function, so we replace f of minus y by f of 1. So this is the definition of even function. So again I can change the order of limits, so that minus will be dissolved in that, so it will be integration from 0 to pi of fy, or you can write it as fx dx. So variable does not matter here. So plus, that is integration from 0 to pi of fx dx, or you can write it as 2 times integration from 0 to pi of fx dx. So simply, if f is an even function, integration from minus pi to pi of fx dx is nothing but 2 times. So integration from 0 to pi of fx dx. So that is first remark, and its proof is here. Yeah. So you can refer this proof. Very simple. So that is first remark. Second remark. See, what is second remark? If f is an odd function, so in that case, what is integration of? So integration from minus pi to pi of fx dx. So then integration from minus pi to pi of fx dx will be just 0. So here also you can check the integration here, because let us see. So since f is odd function, so here you will get, so instead of f of y, so f of minus y will be again minus, so you will get this term minus. So in that case, so you'll get one extra minus here, therefore this term and this term will cancel to each other, and you'll get the value of resulting integration 0. So since f is odd function, so resulting integration will be 0. Very simple, so you can check it. So next, there is third remark. So remark is that if f is even function, if f is an even function and g is, so f and g are both even, then what happens? F is an even function and g is an even function, or if you can write f is an odd function and g is also odd function, and g is also odd function, Then what about f into g? So then f into g is an even function. That is, odd into odd is even, and even into even is again even. So that is third remark. Fourth remark is that, so one function is odd function and other function is even function. So in that case, what will be their product? So odd into even will be again odd. So if f is an odd function and g is an even function, then f into g, that is product of f and g, is an odd function. So that is fourth remark. So next, yeah. So next is definition of Fourier series, but we'll see a definition in next lecture because we have to see some examples on it. So I will stop here, and remaining part we'll see